الشغلة الوحيدة إذا بتسمع بيب روان بدك تعملي لهم أدمت.
اوكي.
اوكي في هنا
بلش؟
تعالي هلا just to show you this is you put full screen here, full screen, and you can just use this to change, or you can use this.
لما اسمع البيب وين احط؟
بس لما تسمع البيب تطلعي برا هنا تعملي admit configuration مكتوب someone trying to join, so you do admit.
ماشي.
طيب مقدمة سريعة. روان تدرس في جيوليتش في ألمانيا تحت البرنامج اللي هو بتعمل دكتوراه. هي معها بكالوريوس زراعة و 2 master degrees, one in Holland, one in Germany, and she is close to finishing her PhD, and she will be talking to us about the subject of nanoparticles. So she will speak in English, and hopefully, you do admit, and then you can go back and do this.
إن شاء الله تعلمت اللغة الألمانية يا روان.
Yeah, sehr gut.
Sehr gut, das
freut
mich.
Got his PhD also in Germany.
Ja.
Geology.
Ich bin schon davon ausgelöst, ja.
Dankeschön.
Willkommen.
Dankeschön.
Okay.
Yeah. Shall I start?
Yeah.
Okay. Yeah, my name is Rawan, as Dr. Mazen said. I'm originally from Hebron, from south of Hebron, from Bahia. And I did my master degree in Bonn, at Bonn University in Germany, in agricultural science and resources management. And then I did another degree at Maastricht University in the Netherlands. But this one has focused on sustainability, science, and policy. And I'm now in the course of finishing my PhD, which has nothing to do with my first master, but at least something to do with the environment. So my PhD focused on use of nanoparticles for water remediation. And actually I work now with iron nanoparticles, not only iron, of course, for their safety to the environment. I do my master at Juelich Forschungszentrum in Germany, and I am registered at RWTH in Aachen University. So we go. So the whole situation or the whole problem starts from the water scarcity, which of course concentrated, as you see on the map, in the Middle East and North Africa. And by numbers, if we talk about water, the whole planet is covered. 70% of the whole planet is covered with water, but only 3% of this water is can be used for as a fresh water for human use. However, there's like 500 million people who use water twice or higher than we get from the rain or replenished by the rain. Talking about the quality of the water, there's a high number of people who die, like more than 800,000 people who die from contaminated water. And we talk about like 80% of illness are caused by dirt water or by wastewater. Of course, water I mean, the scarcity of water and the quality of water can affect the sorry, can affect the economic situation of any country or at household level. Of course, Palestine, it has special situation because of the occupation, of course, but also because Palestine is originally scarce in water. So for the international standards, every human being is or the water, the minimum water consumption for everyone should be 100 liters per day. But the situation, of course, in the West Bank and in the sea area is different. So people consume less than even 50 liters per day. The water should be also should be accessible at any time it's needed. In Palestine, in West Bank, there's more than 100 communities are still not connected to networks, to water networks. The same situation in Area C. In normal cases, the water shouldn't cost more than 3% of the household income, but in Palestine, more than 18% of the total family income goes for water. So there's many sources for wastewater, or where does wastewater come from? It comes from the industrial facilities or the factories, and this kind of water, it's the we can see that the most complicated one, because it depends on the type of the industry. So it can release heavy metals, organic chemical pollutants, and pharmaceuticals, and it's really challenging to be treated. The agricultural activities also contribute to the wastewater. For example, the fertilizers or the pesticides used in agriculture, and also the pathogens come from livestock farms. The third source is the domestic sources. That means the water that comes from the houses, and also this type of water contain pathogens, organic and inorganic pollutants. Inorganic pollutants like nitrogen, phosphorus, heavy metals. Organic like the solvents used in the house, the chlorine and other things. Of course, all of this water, if not treated, it will end up in the rivers and in the groundwater, which is used for domestic consumption or for used as drinking water. I just saw some examples for water pollution from Palestine. As you see here, from Gaza City, some children playing in wastewater. And yeah, Gaza, it has a special situation by now. I don't think that there's water, like except the one that in the bottles that is good to be drank. And here we see another example from wastewater, seepage of wastewater, but this one is discharged by the settlements into Olivetry, but of course it has the same, it has finally the same destination to the groundwater. We see here some pipes for wastewater, just running in the fields or in the on the ground. This photo taken in Sulfate Governorate. And another problem is the garbage dump, and this one I believe it has been taken here around Bethlehem. So you can imagine how much pollutants coming out of these sources. So the classical treatment of wastewater depends on different steps, and each step is costly and complicated. Here is a wastewater plant in Nablus. I believe this was constructed by a German project. So the classical treatment of water composed of, as I said, from steps. The first one is screening, is by separating the big, can I say, I don't know, or the sludge from wastewater, and then it is exposed to aeration and treated by chlorine, and in the coagulation also treated by other chemicals. They let the water sediment and then filtrated by sand. And of course, other supplementary steps has to be taken to get not, I can't say clean water, but cleaner than before. However, the conventional treatment of wastewater is not a guarantee that the water now is empty or free of pathogens, because all of these steps cannot capture the pathogens exist in the water. That's why there is now technology is being implemented in Europe, and also in the advanced countries. It's called the nanotechnology. So it's about the use of nanoparticles for water remediation. Why? Because nanoparticles simply they are have special characteristics. One of these characteristics is they have a large specific surface area, and thus they have more sites to capture the pollutants like pathogens, ions, and other pollutants. And they have strong reactivity. So they capture the pollutants either by adsorption, through ions exchange between the pollutants and the nanoparticles, or by precipitation, where the pollutant is by gravity is sediment on the surfaces of the nanoparticles, or by oxidation. Some nanoparticles have the ability to be poisonous for the pathogens. That's why when they come into contact with each other, the pathogens die. Of course, nanoparticles are highly mobile in solution, also in ground. I mean, in the soil or in porous media, and they prove that they are really effective in heavy metals and organic pollutants or other inorganic pollutants removal. How they work? There are different categories for the removal of the pollutants by nanoparticles. The most important one is the adsorption of the pollutants onto the nanoparticle surfaces. The other one is the use of these nanoparticles with the aid of the sun or the ultraviolet light in water treatment. The third is the disinfection of water, and this is exclusively for the pathogens. And of course, the nanomembrane filtration. For the adsorption of the nanoparticles, this photo is taken by SEM. It's very complicated microscope to see the nanoparticles, because they are in size can be like 100 nanometer. So the removal of contaminants occurs when the sorbate, and in this case the sorbate is the water pollutants or the ions in the water, adsorbed on the surface of the sorbent, and the sorbent here are the nanoparticles. Of course, there are attractive forces and what's called the filtration theory behind the whole mechanism, and it's very complicated. Some examples of the nanoparticles are the iron nanoparticles or the iron oxide nanoparticles, zinc oxide or magnesium oxide, also aluminum oxide, titanium oxide, dioxide, which is used in photodegradation, also silicon-based nanomaterials or carbon nanotubes. I would like, can I ask you to turn your microphone off, please?
Oh.
Thank you. Yeah. So I would like to focus on the iron-based nanoparticles. They are really special because they are environmentally friendly, and they can treat different type of pollutants using different mechanism. So they can degrade the organic matter, for example, when they come in contact with it. They can reduce the nitrate and the nitrogen to another compound that it is more safe for the environment, or they can reduce the heavy metals to other compounds. And they proved that they were efficient for treatment of contaminated soil, not only water and the groundwater, and they have the ability to migrate below the ground. So if you see here, I don't know if you can see here, if they pump the nanoparticles into the ground, for example, we have here contaminated site or polluted site. They just inject the nanoparticles in this site, and then the nanoparticles, the iron nanoparticles, can do the job. I will come to an example later. However, of course, there is some factors that control this, the whole adsorption process. Of course, the size and the surface area. When the surface area is higher, then we have more site to capture more pollutants. And the surface physiochemical properties, for all of the nanoparticles, they have kind of roughness. So this play a very important role for, as you see here, if you see the zinc coming in like in cave shape. So if we have this high roughness in the nanoparticles, pollutants can be physically trapped there, and this is what we called sedimentation. So the other thing that these nanoparticles, they tend to aggregate. So because they have magnetic feature, the iron nanoparticles, they tend to aggregate together, and this is not good for their function, because once they aggregate, the surface area will decrease, and they will not be exposed to pollutants to be trapped or adsorbed. Of course, media chemistry, like the water, the solution, or the porous media also play an important role. And the solution chemistry, like pH, for example, increase in pH, درجة الحموضة. If we increase the pH, more adsorption will occur. But if we decrease the pH, then the ions, the hydrogen ions, will compete the pollutant ions to be trapped to the nanoparticles. The incubation time and the adsorbent dose. For example, in my study, I found that if the dose of the adsorbent is higher, then more pollutants will be captured. And if we increase also the time of contact between the nanoparticles and the pollutants, more removal will occur. To overcome this factor, which is the aggregation, now the any research has to do with iron nanoparticles, focus on coating of the nanoparticles. For the coating, they use organic compounds like starch, nasha. And what does this coating actually do is to enhance the reactivity of the nanoparticles and separate them. They increase their dispersibility in the solution and prevent their aggregation and facilitate the separation of the, here it stands for the zero-valent iron nanoparticles from the degraded system. And of course, protect the nanoparticles against rust. So if you see here, for example, here is solution of the iron nanoparticles. Once you have like magnetic, you can collect them all from the solution, and what remains is only water. The other category, yes, this is a case study actually from Germany. So the place was in Bornheim, and this place was contaminated with tons of organic pollutants. It has to do with the chlorine. It was contaminated from industrial zone, and this compound was spread over an area of several square kilometers and to the depth of 20 meters. So it was complicated how to treat this area. So what they have done is they used technology, or not a technology, but yeah, a method of pump and treat. Get this pollutant out of the air of the ground and then treat it. And they have done this for 14 years. So when they calculate how much time to finish all the job, then they needed like 50 years to remove all the contaminants, with a cost of like €1 million to remove only 5 tons. For the rest, so 2 tons, about 1 to 2 tons of this pollutants remain on the ground, and they use the zero-valent iron nanoparticles. The reduction in contaminant increased, like they achieved till 95% of the contaminant, removal of the contaminant just in 1 month, with a cost of more than like, yeah, 366 euro per square meter. And you can see here from the photos how the contaminants was in the ground, and then after 2 years, yeah, less contamination, here almost clean. The other category is the photo decomposition using nanomaterials, and this is rely on the, sorry, you cannot see here, but this, yeah, this technique relies on the ultraviolet radiation or the sun. So yeah, it is supposed to be eco-friendly technique, though it's used titanium dioxide, which is not environmentally friendly nanoparticles. And this type of treatment is used for persistent organic pollutants like pesticides or compounds come from medical factories. So how this works? So when the light or the ultraviolet fall on the nanoparticle, so they use titanium dioxide nanoparticles. When the light hit these nanoparticles, it will release the electron and what's called the hole in the conduction band and valence band. And these, they migrate to the surface or the oxide surface of the nanoparticles, and they start to react with the surrounding molecules like the oxygen or the water. Once they come into contact with these compounds, they start, of course, they produce what's called superoxide ions or OH radicals, and these are not, yeah, they are poisonous to the pathogens like E. coli here. But as I said, titanium dioxide is, though it's very efficient in this technique, but it has other disadvantage, because at the end they cannot collect it from the water or from the solution. The other category is the disinfection by nanomaterials, and they use the zinc oxide for that, which of course cause fatal damage to the microorganisms, because when it comes in contact with water or oxygen, it produces H2O2, and this compound, it's poisonous. Or they increase the zinc ions, which damage the membrane and penetrate the intracellular contents of the cell of the bacteria, or either by the direct contact of the nanoparticles, the zinc oxide nanoparticles, with the bacteria cell, and change in the micro environment here of the bacteria cell. The nanomaterials now is, this one is the very new subject, is simply to use the nanomaterials like in a small scale, like this is a membrane, or produce a membrane of the nanoparticles that it's attached to. I don't know how to say about that, but it's like a filter. And yeah, when it's fed by waste solution, the nanoparticles trapped all the contaminants. And for this, mostly they use the iron nanoparticles, not iron oxide or magnetite, because it's safe. Of course, for the nanoparticles, there are a couple of limitation. The first one is that dispersion in the solution or in the groundwater, the retention and recovery. Once they spread the nanoparticles like the titanium dioxide, they cannot collect it again, or the loss of activity over time. They become saturated and no more efficient to collect more pollutants. Of course, the realistic condition, or the condition of the water, condition of the soil, plays an important role. The cost balance, some nanoparticles are really expensive, but for iron is not the case, and can be simply produced in any laboratory with basic equipment. And still there is less is known about their toxicity. There are a lot of publication, but some nanoparticles toxicity is not prevailed yet. That's why
how do you remove the pollutant that's adhered to the nanoparticles, or is this a one-time use?
Once the nanoparticles are saturated, they cannot be they can be reused if you manipulate the chemistry of the solution. This is what we call the desorption. So if, for example, the pH, the temperature. So nanoparticles are not, it's not like the magic solution, because of course they are harmful for the quality of life of humans, animals, and plants. There are some researchers that they found, for example, most of the researchers for the nanoparticles to see their ecotoxicity is done on the fish, and they found that some nanoparticles are accumulated in the body of the fishes, and or they are suspended, or they end in the food and drinking water. Of course, the uptake of the nanoparticles by living organism can induce toxicity effects, as I said, for the zinc oxide nanoparticles, they are originally poisonous for the cells, and this can damage, of course, their function. As I said, the titanium dioxide is hardly biodegradable, thus it's still a challenge to retain it from the solution where the adsorption process has been taken. So that's it for me. Thank you for your attention, and yeah, I hope I had present something that's good. Any question?
كنت بدي أسألك سؤال بس.
تفضل.
بالنسبة لهذه الطريقة، هل يعني غالية، يعني أغلى من الطرق العادية، ولا يعني accepted أكثر، يعني قصدي أرخص يعني ممكنة؟
هلا هاي الطريقة طبعا النانو بارتيكلز يعني عندهم يعني أكثر من نوع، من الذهب نانو بارتيكلز للفضة للآيرون الزنك. زي ما حكيت الآيرون هو من أرخص الآن نانو بارتيكلز اللي ممكن الواحد يستخدمها، وبقدر الواحد إنه يصنعها في المختبر. حتى في أبحاث إنك تقدر to extract the nanoparticles from the leaves of the plants. إذا هذه الطريقة is efficient، مثلا في المثال اللي فرجيتكم إياه احتاجوا ل 3 طن of solution of nanoparticles عشان يعالجوا 2 tons of waste of pollutants. So you need a lot of nanoparticles. Is efficient? Yes, it's more efficient than the classical treatment, because at least you guarantee that you will get no pollutants at the end in the water. هاي الطريقة كمان سوري بس بدي أضيف هاي النقطة، ممكن تستخدم يعني على الهاوس هولد. مثلا إذا مثلا كل بيت عنده وحدة تنقية مياه، ممكن يستخدم مثلا، ما بحتاجش، بتخيلش إنه بحتاج كمية كبيرة من النانو بارتيكلز. مثلا بدنا نصفي المي اللي جاي من المطبخ مكان ثاني، يعني ما بحتاج، بتخيلش إنه بحتاج كثير نانو بارتيكلز لسمول سكيل يونت.
يعني يا سيدة، أنا اللي فهمته إن النانو بارتيكلز بتقولي أنت من الحديد، يعني شو يعني من الحديد؟ يعني حديد عادي هي بتكون؟ نعم بودرة؟
نعم هي بودرة. عشان نحكي نانو بارتيكلز يعني بنحكي بالسكيل تبع النانومتر. اوكي خلص، لما بعد النانومتر بيجي المايكرو والميلي بتبطل نانو بارتيكلز. فمثلا النانو بارتيكلز اللي بشتغل فيها انا الحديد هي بودرة، بس ما بتقدرش تشوف كل سنجل نانو بارتيكل. يو نيد very advanced microscope يعني عشان يكبر لك بملايين المرات عشان تقدر تشوف.
ايوه يعني بودرة حديد.
بودرة حديد ممكن تستخدم، مش البودرة الحديد اللي موجود، يعني لازم تتصغر لحجم النانومتر. Actually it's they use chemical يعني تفاعلات كيميائية، بعدين بالترسيب ترسب يعني الحديد، مش انه بيجيبوا حديد و يعني بطحنوه وبطلع منه نانو بارتيكلز.
يعني في عندنا برادة الحديد يعني ما بتستخدم.
أنا ضد هاي الفكرة إنه ما بنستخدمهاش. بنقدر نستخدمها لأنه الحديد هو برادي، وهو يعني جزء كبير أو جزء صغير لسه بيعمل نفس التفاعلات الحديد اللي بيعملها. أوكي بغض النظر عن حجمه، بس الحجم هون بيلعب دور أكبر في أخذ كمية أكبر من البوليوتنس.
يعني لو تعطينا مثال، مثلا متر مكعب من الويست ووتر قديش بده من البودره هاي؟
ما عنديش فكره، ما عنديش فكره عنها يعني هذا الشيء التطبيقي، لانه ما يعني كل الابحاث اللي بقراها عن الابحاث يعني التطبيق في المختبر، بس في الفيلد ما عنديش فكره بصراحه. بقدرش اعطيك رقم واقول لك هيك بحتاج وانا ما بعرفش.
هو بدنا نعرف،
بس هي المثال مثلا اللي شفنا انه ل 2 طن من البوليوتانس يحتاجوا 3 طن من السوليوشن، فيك تركيز 5 بتذكر هذا كان 5 جرام لكل لتر تركيز حديد.
5 جرام لكل لتر
5
يعني
جرام I
يعني
don't think that you need a lot.
يعني مش كثير.
لا، بس اللي بدي احكي لك اياه انه هاي النانو بارتيكلز هلا يعني عامل ثوره في مش بس في الووتر تريتمنت، بس كمان في الميديسن، في الصناعات. فاتس هوت توبيك.
احنا مش سامعينك يا مازن.
انا راح اعيد لك التعليق.
ضروري.
Because the particles are so small, rusting can be mechanism of degrading particles that we use.
الدكتور بيسأل انه زي الفيت يعني مصير هاي النانو بارتيكلز بعد ما نستخدمها.
مزبوط والله.
هلا في ابحاث انه ممكن يرجعوا يجمعوا هاي البارتيكلز يعملوا منها اشي ثاني يعني. يعني خاصة أنا ضد إنه يستخدم النانو بارتيكلز على طول في الأرض، لأنه راح تضلها في الأرض وتنتهي كمان في الجراوند ووتر. بس إذا هاي النانو بارتيكلز على سبيل المثال استخدمناها في وحدات لتنقية المياه، تقدر في الآخر تجمعها and you store it or you I don't know convert it to
يعني بصير زيها زي سلوتش يعني.
Accelerating its rusting.
شو بيقول؟
بحكي عن انه يعني بعد ما تنجمع ممكن انها تصدي رست، ممكن انها تصدي. بس الكوتينج اللي حكيت عنه هم هلا ما بيستخدموش الايرون نانو بارتيكلز without كوتينج، لانه عنده قدره عاليه على يرجع يتجمع مع بعض. فاصلا اذا حطيته في سوليوشن مع بوليوتانس عنده ماجنتيك فيتشر انه يرجع كله يتجمع مع بعض. شكرا للحضور كمان مرة.
شكرا لك. شكرا.
That's it. Shall I?